Most cosmology textbooks begin with the same assumption. The universe is vast, open and unbounded. A 93 billion light-year expanse of space and time that began 13.8 billion years ago from a single point of infinite density and has been expanding outward ever since. That is the standard model. It is taught in universities. It is repeated in documentaries. It is, as far as most physicists are concerned, the working framework. But in 2010, a Polish theoretical physicist named Nikodem Poplawski published a paper out of Indiana University that quietly proposed something different, not as a thought experiment, not as science fiction. As a mathematical derivation, peer-reviewed, published in a physics journal, and listed by both National Geographic and Science magazine, among the top 10 scientific discoveries of that year. His conclusion: our universe may be the interior of a black hole. Almost nobody read it. So why did the numbers in Poplawski's model match the observable universe exactly? Not approximately exactly. And why has that correspondence never been fully explained? Why does the theory also solve three of the deepest unsolved problems in physics simultaneously? And why did a telescope launched into orbit around the Sun in December 2021 find, in February 2025, precisely the signature that the theory predicted? In the rotation of 263 galaxies, nobody was looking at for that reason. To understand what Poplawski found, you need one number. It was calculated in 1916 by the German physicist Karl Schwarzschild, working at the Russian front during the First World War, doing mathematics in the trenches. He was solving Einstein's field equations, which had been published only weeks earlier. What Schwarzschild found was a radius, a specific distance from the center of any object below which gravity becomes so strong that nothing, not matter, not light, can escape. That radius depends on one thing: mass. The more mass, the larger the radius. This is the Schwarzschild radius, and it is the boundary of a black hole. For the Sun, the Schwarzschild radius is about 3 kilometers. Compress the entire mass of the Sun into a sphere 3 kilometers across, and you have a black hole. For the Earth, the radius is about 9 millimeters. A marble-sized Earth would collapse into a singularity from which nothing returns. Now apply the same formula to the observable universe. Take the total estimated mass energy of everything we can detect, all the galaxies, all the gas clouds, all the dark matter, everything, and calculate the Schwarzschild radius that mass would require. Then measure the actual radius of the observable universe, the Hubble radius, which is approximately 13.8 billion light-years to the edge of what light has had time to reach us from. They match. Not roughly, not as an order of magnitude coincidence. The Hubble radius of the observable universe is equal to its Schwarzschild radius. The universe is exactly the right size to be a black hole, and no one has produced a satisfying explanation for why that is, if it means nothing. The standard response among physicists is that this is a coincidence of cosmological models and units, that the equality follows from certain definitions and doesn't carry physical meaning. However, Poplawski's point was more specific than that. He was not noting the numerical coincidence alone. He was noting that every observable property of our universe is consistent with being the interior of a black hole. And that Einstein-Cartan gravity, a well-established extension of general relativity, provides a precise physical mechanism for how it got that way. Here is what makes that claim harder to dismiss than it first appears. A black hole large enough to contain a universe would not look or feel like the black holes described in science fiction. Scale matters. A black hole with approximately 400 million solar masses would have an average interior density roughly equal to the density of air at sea level. You would not be compressed. You would not feel a wall. If you were falling through the event horizon of a sufficiently large black hole, you might cross it without any physical sensation at all. No surface, no boundary you could perceive, no signal that you had passed the point of no return. Scale this up to a universe-sized black hole, and the event horizon crossing would be utterly imperceptible to anything inside it, which means the question of whether we have already crossed one is not a question our instruments can answer by looking outward. It is a question about the structure of the system we are already inside. But what makes Poplawski's model different from earlier versions of this idea is not the size argument, it is what happens at the center. General relativity predicts that matter collapsing inside a black hole falls toward a singularity, a point of infinite density where the equations break down and physics stops working. The Big Bang, run backward in time, also ends at a singularity. Physicists have known for decades that these two singularities are mathematically the same object. A point where density is infinite, temperature is infinite, volume is zero, and every law of physics stops describing anything. Almost nobody asks the obvious follow-up question: if they're the same mathematics, why do we assume they're different events? The standard answer is that one is a gravitational collapse and the other is a cosmological expansion, and the arrows of time run in opposite directions. However, that answer only moves the problem. It doesn't solve it. You still have two infinities, and infinities, as Poplawski put it, are unphysical. They are not real. They are the sign that a theory has been pushed beyond its range of validity. Einstein-Cartan gravity resolves this by adding one thing that general relativity leaves out: the intrinsic spin of fermions. Fermions are the particles that make up matter: quarks, electrons, protons, neutrons. They have a property called spin, which is a quantum mechanical form of angular momentum. In standard general relativity, the antisymmetric part of the connection that describes space-time, the torsion tensor, is constrained to zero. Einstein-Cartan theory removes that constraint and makes torsion a dynamical variable. The result is that at densities above approximately 10 to the power of 45 kilograms per cubic meter, densities that exist inside black holes and only inside black holes, torsion stops being negligible. It becomes a repulsive force. It acts against gravity, and it prevents the formation of a singularity. What happens instead is this: the collapsing matter inside a black hole does not fall to a point of infinite density. It reaches an enormous but finite density, far beyond anything in ordinary physics, but not infinite. And then it bounces. It rebounds. It forms an Einstein-Rosen bridge, a wormhole, to a new and separate region of space-time. A new closed, expanding universe begins on the other side of the event horizon. Quantum particle production in the intense gravitational field near the bounce generates enormous amounts of matter and produces a brief period of exponential expansion, inflation, without requiring any hypothetical fields. The Big Bang, in this model, is not a beginning, it is a rebound. That rebound also solves a problem that has troubled physicists since the 19th century: the arrow of time. The equations of physics, Newton, Einstein, quantum mechanics, work equally well in both directions of time. Nothing in the fundamental laws distinguishes the past from the future. Yet we experience time as flowing in one direction only. Entropy increases. Causes precede effects. We remember yesterday and not tomorrow. The question of why time has a direction has no good answer inside standard cosmology. Poplawski's answer is precise. In his model, the arrow of cosmic time of a universe inside a black hole is fixed by the time asymmetric collapse of matter through the event horizon of its parent universe. The matter that formed our universe fell through a boundary in one direction. That direction defines our time. We did not create the arrow of time, we inherited it. From somewhere we cannot see, through a boundary we cannot detect, from an event that happened before our physics began. But this is also where the theory's most disorienting implication emerges. If torsion prevents singularities, and if every black hole forms a new universe on the other side of its event horizon, then every black hole in our universe is doing this right now. Sagittarius A star, the supermassive black hole at the center of the Milky Way, with a mass of approximately 4.15 million solar masses, may contain an entire expanding cosmos inside it at this moment. Completely isolated, unreachable, invisible from our side, and governed by a version of physics slightly different from our own. Every stellar mass black hole in our galaxy, every quasar in the observable universe, every gravitational collapse we have ever detected. Each one in this model is a universe being born. The physicist Lee Smolin at the Perimeter Institute for Theoretical Physics in Waterloo, Canada, took this logic further than anyone else. In 1992, he published a paper in Classical and Quantum Gravity, Volume 9, pages 173 to 191, proposing what he called cosmological natural selection. In 1997, he expanded the argument in a book called The Life of the Cosmos, published by Oxford University Press. Smolin's argument is this: if baby universes inherit the physical constants of their parent universe, but with small random variations, the way biological offspring inherit genes but with mutations, then there is a population of universes subject to selection pressure. Universes that produce more black holes have more offspring. Their physics is replicated more often. Over billions of generations of cosmic reproduction, the population of universes is dominated by those whose physical constants maximize black hole production. Our universe's constants, the strength of gravity, the mass of the electron, the fine structure constant, are not arbitrary. They are, in Smolin's model, the result of selection. The outcome of a process that has been running for far longer than our universe has existed. What makes this more than a philosophical exercise is that it makes falsifiable predictions. Smolin noted that the same physical constants that maximize black hole production also happen to be the constants that allow stars to form, chemistry to exist, and life to emerge. The universe is not fine-tuned for life as a special favor. It is fine-tuned for black holes. Life is a byproduct of that optimization. The universe that produced us was not trying to produce us. We are the residue of a process aimed at something else entirely. However, Smolin's theory has critics, serious ones. The physicist Leonard Susskind argued that Smolin's mechanism requires information to be transferred across a black hole's event horizon, from parent universe to offspring universe, and that the last decade of black hole physics has shown no such transfer is possible. Additionally, Smolin's original prediction was that no neutron star should exceed 1.6 solar masses. Neutron stars of approximately 2 solar masses have since been observed. The theory may need revision, or it may be incomplete. What it is not is untested. But the more immediate question, the one that does not require waiting for a complete theory of quantum gravity, is whether the universe we live in shows any signs of having an origin inside a rotating black hole. A rotating black hole has an axis. That axis defines a preferred direction in space. If our universe was born inside one, we might expect that preference to be imprinted somewhere in our universe's structure, in the way galaxies rotate, in the statistical distribution of angular momentum across cosmic scales. This would be a signature. It would not be loud. It would be subtle, detectable only in large statistical samples, but it would be there. On February 17, 2025, a paper was published in the monthly notices of the Royal Astronomical Society. The author was Lior Shamir, Associate Professor of Computer Science at Kansas State University. The data came from the James Webb Space Telescope's Advanced Deep Extra Galactic Survey, JDES. Images of the farthest reaches of the observable universe, galaxies billions of light years away, closer to the beginning of cosmic time than to the present. Shamir's team analysed 263 galaxies for which the direction of rotation could be determined. Of those 263, 158 rotate clockwise, 105 rotate counterclockwise. In a genuinely random universe with no preferred axis, the expected split is 50-50. The probability of observing an asymmetry this strong or stronger by chance alone is 0.07%, not 7%, 0.07%. Poplawski, contacted by space.com for a response, said, "A preferred axis in our universe, inherited by the axis of rotation of its parent black hole, might have influenced the rotation dynamics of galaxies, creating the observed clockwise-counterclockwise asymmetry. The discovery by JWST that galaxies rotate in a preferred direction would support the theory of black holes creating new universes. This is not a retrofitted explanation. The signature JWST found is exactly where the theory said to look, and exactly of the kind it predicted. A universe born from a non-rotating black hole would show no asymmetry. A universe born from a rotating one would. The data shows one. That is the situation as of 2025. Shamir himself was careful. Alternative explanations exist. The Doppler shift from the Milky Way's own rotation could introduce observational bias. The Goods S field, where Jade's observations were concentrated, is located near the southern galactic pole, a region where prior surveys had already detected elevated clockwise asymmetry. The result is real. Whether its cause is a parent black hole is not yet confirmed. However, it has also not been explained by anything else. And this is where the theory's final layer surfaces, the one that makes the black hole universe not just a cosmological claim, but a statement about the nature of reality itself. In 1993, theoretical physicist Gerard T. Hooft proposed what became known as the holographic principle. It was expanded by Leonard Susskind and has since become central to theoretical physics, particularly in the study of quantum gravity. The principle holds that the maximum amount of information that can be stored within any volume of space is not proportional to that volume. It is proportional to the area of the boundary surrounding it. Information in 3 dimensions is encoded on a surface in 2 dimensions. The universe, in this view, is not fundamentally 3-dimensional. It only appears that way from inside. The direct connection to black holes is where this becomes relevant here. The entropy of a black hole, the total information content of everything that has ever fallen into it, is given by the Bekenstein-Hawking formula, derived in the 1970s by physicists Jacob Bekenstein and Stephen Hawking. That formula relates entropy to the surface area of the event horizon, not the volume inside, the surface. If we live inside a black hole, the boundary of our universe, the event horizon of the black hole that contains us, is not just the edge of what we can see. It is the surface on which every piece of information defining our reality is encoded. Every particle, every field, every interaction that has ever taken place in our 3-dimensional experience of the cosmos is, in this interpretation, a projection of data written on a 2-dimensional shell somewhere above us. A shell we cannot reach, a shell whose existence we cannot confirm by looking outward, because looking outward from inside a black hole never gets you to the event horizon. You are always inside it. Our 3-dimensional reality, the depth, the volume, the sense of physical space that every organism on this planet takes as the fundamental texture of existence, may be the readout of a lower dimensional encoding we will never access directly. This is not a metaphor. It is the mathematical implication of the holographic principle applied to a black hole universe. There is one more thing the theory addresses. One of the deepest unresolved problems in physics is the matter-antimatter asymmetry. The Big Bang should have produced equal amounts of matter and antimatter, equal quantities, equal energies, equal and opposite. When matter and antimatter meet, they annihilate. If the universe began with equal amounts of both, nothing should exist. No stars, no planets, no atoms, just photons. Yet we live in a universe made almost entirely of matter, with antimatter appearing only in trace quantities, in cosmic ray detections and particle accelerator experiments. Where did the antimatter go? The standard model offers no good answer. However, Poplawski's torsion-based framework proposes one. Because of the way torsion interacts with fermion spin at the extreme densities of a black hole bounce, matter and antimatter do not decay symmetrically. Matter decays into the familiar quarks and electrons that make up everything we can touch. Antimatter decays differently, into particles that interact gravitationally but not electromagnetically, that pass through ordinary matter without interaction, that accumulate in halos around galaxies without emitting or absorbing light, dark matter. Physicists have been searching for dark matter directly since the 1980s. Every underground detector, every satellite instrument, Every particle collider experiment aimed at producing it has returned nothing. Dark matter has not been found because it does not interact with the instruments built to detect it. In Poplawski's model, the reason is simple. Dark matter is the antimatter that standard cosmology says has to be somewhere. It decays differently because of torsion at the bounce. It accumulates where the mathematics says it should, in gravitational halos around galaxies, making up approximately 27% of the total mass energy of the universe. And it will not show up in any detector designed to find a weakly interacting particle, because that is not what it is. Additionally, the accelerating expansion of the universe, the fact that galaxies are moving apart from each other faster and faster, a phenomenon discovered in 1998 by astronomers Saul Perlmutter, Brian Schmidt and Adam Riess, for which they were awarded the Nobel Prize in Physics in 2011, is currently attributed to dark energy. Dark energy is a placeholder, a name for something that accounts for approximately 68% of the total energy content of the universe, and is otherwise completely unexplained. No one knows what it is. It was added to cosmological models because the math required it. Poplawski's torsion produces a cosmological constant naturally, an outward pressure that arises from the same physics that prevents singularities at the bounce. The accelerating expansion of the universe, in this model, is not a separate phenomenon requiring its own unexplained ingredient. It is a consequence of the same torsion that replaced the Big Bang singularity with a rebound. The force pushing everything apart is the echo of the same physics that created us. 3 unsolved problems, 1 framework: dark matter, dark energy, and the arrow of time, the 3 largest open questions in cosmology, each addressed by the same modification to general relativity that Schwarzschild might have been able to write down at the Russian front in 1916. If he had known that spin-torsion coupling was what he was missing. He didn't know. Neither did Einstein. The Einstein-Cartan theory was developed over decades by mathematicians and physicists after Einstein's death, refined by Tom Kibble and Dennis Sayama in the 1960s, and extended to cosmology by Poplawski in 2010. The mathematics has been there for a long time. The willingness to follow it to its conclusion has been slower to arrive. And this is where the theory becomes something more than a model of the universe's origin. Lee Smolin, standing on the shore of a lake near Penn State in the early 1990s, was trying to disprove his own idea. He had thought of cosmological natural selection while sailing, written it down, and then spent months attempting to find a flaw that would kill it. He later said he was shocked that he couldn't. I was shocked that I couldn't kill it. The physics kept surviving contact with the evidence. The idea that constants are selected through reproduction, that our universe is one of a vast and growing population of universes, each slightly different from its parent, that the fine-tuning problem has a Darwinian solution. All of it kept passing the tests he threw at it. What he was really asking, without quite framing it this way, was whether the universe is the kind of thing that can have a reason for its properties, whether physics evolves, whether the laws of nature are contingent, the result of a history, rather than necessary, the way they simply had to be. Biological natural selection replaced necessity with history. Smolin was asking whether the same replacement applied to physics itself. The answer is not confirmed. What is confirmed is that the question is legitimate, that the mathematics is consistent, that JWST has found a pattern where the theory predicted one, and that 3 of the largest unsolved problems in physics have proposed solutions inside a single framework that begins with one assumption: that the event we call the Big Bang was not the beginning of everything, but the interior view of a gravitational collapse that happened somewhere else. There is something else implied by this that is harder to articulate but harder to ignore. If the theory is correct, then the universe you are in right now is not the only one. It is one in a chain. A chain that may have no beginning. Each universe born from a black hole in a parent universe that was itself born from a black hole in a grandparent universe. An infinite regress of cosmic births. Each one closed off from the others. Each one containing within it the compressed remnant of a question it will never be able to ask in full. We are not the first universe to have stars. We are not the first universe to have physics. We are, in all likelihood, not the first universe to have something like life, wondering about its origin, building instruments to detect the signature of where it came from, and finding, in a survey of 263 distant galaxies, in a statistical asymmetry of 158 to 105, in a rotation preference that has a 0.07% probability of occurring by chance. What might be the faintest possible fingerprint of a parent we cannot see in a universe we can never visit? Through a boundary we crossed before we existed. We didn't invent the question of where we came from. We inherited it, along with the direction of time, along with the rotation of our galaxies, along with the laws of physics that allowed us to form, to persist, and to ask the question at all. The universe is not the answer. It is the question, passed down from somewhere we will never reach, through a door that has been closed since before the first second of cosmic time. If this video gave you a different way of thinking about the universe and your place in it, consider subscribing. And I want to know, if the theory is correct, and every black hole in our universe is a universe being born, does that change how you think about what Sagittarius A star is? Does the black hole at the center of our galaxy become something different to you, knowing what might be on the other side of it? Let me know in the comments.